Hello again and welcome to a new lecture in which we will solve a couple of examples related to the design of member under axial tension. So in the first example, we will consider a very simple truss made of three members, A, B, B, C, and AC, which is supported at A and C, simply supported by a pin and a roller, and having a force with a magnitude of 100 kilonewtons acting vertically at B. Member AC is 2 meters long, and the angles at A and at C are 60 degrees, which makes the entire triangle an equilateral triangle. The three members in this truss are made of steel that has an yield stress of 300 megapascals and a modulus of elasticity equal to 200,000 megapascals, which is of course typical for steel. The load factor for design in tension is 2.0, and we are asked firstly to design member AC by using a rectangular cross section which has the longer side A and the shorter side B, and the sides of the cross section are such the longer side is 3 times the shorter one. In the end, once we have determined the sides of this member, we need to calculate the elongation of this member. So let's start with the first question. Assume that by using the method of joints, we have determined that the force in member AC equals to 28.87 kilonewtons in tension. I'm not showing the actual calculations because we have done that already, and now we need to just exemplify how to perform the design. This force is a specified force, so we have to calculate the factored force because this is a design problem. So the factor force in member AC is double the specified force, since the load factor is equal to 2, and that leads to a force equal to 57.74 kilonewtons. From here we can determine the area that is required, the cross-sectional area of the member required, by dividing the factored load in newtons to the yield stress in newtons per millimeter squared, and we require an area of at least 192.47 millimeters squared. So this area has to equal to 3b times b, and if we calculate b and we round up to the nearest, say, millimeter, b will be equal to 8.0 millimeters. So therefore, the cross-section of member AC will be 24, 3 times 8, 24 by 8 millimeters. Now, secondly, we need to calculate the elongation of this member that has the cross-section that we have just determined. So all we have is plug in the numbers P times L divided by E times A, and remember to use consistent units. And also the calculation of deflections does not need any safety included in it, so we're just calculating the actual elongation, so therefore the force used in the formula is the specified force. This would lead to a member in tension becoming longer by plus 1.504 millimeters. Not that much really. But remember, the first part of the question, determining the size of member AC, was a design question. That's why we use the load factor in that part. The second part of the question, calculating the elongation of member AC, was an analysis type of question, and hence we did not have to use the load factor into this calculation. Now let's go to the second example, in which we have a vertical cantilever truss, as you can see here in this picture. So the truss is 6 meters tall by 3 meters wide, and it's simply supported only at one end, at the bottom, at A and G, on a pin on a roller support. So in general, to solve the forces in this cantilever truss, we can start from the top. We don't need to calculate the reaction forces at the bottom. The question asks for the stress due to the applied forces in member EF, as well as the elongation of member EF. And secondly, we need to design the steel member CD by selecting an equal leg angle section. And the material has an yield stress of 280 megapascals. A load factor of 2 has to be used, and the modulus of elasticity for steel is, of course, 200,000 megapascals. Now we have to determine the member forces. The force in member CE equals to the force applied at C, because the other two members CD and BC are collinear. And then by using a method, for example, of joints, we can solve the forces in member DE, and then in member CD, and finally in member EF. As I said, all starting from the top of the truss, since we don't need to calculate the reaction forces, which are both at the bottom. So now for the first question, let's assume that the area of member EF is 160 millimeters square, given. And for this purpose, the stress in member EF will be equal to the force 26.8 times 10 to the power 3 newtons, negative because this is a compressive force, divided by the cross-sectional area of the member, 160 millimeters square, and that will give us negative 168 megapascals, a compressive stress. In a similar fashion, we can calculate the deflection of that member, and don't forget to use consistent units, and also carry the negative sign of the compressive force, and this will give us an elongation, a negative elongation of 1.97 millimeters, which is an indication that the member becomes shorter, which is of course normal since the member is in compression. For the second part of the question now, we have to factor the specified force in member CD. So 12 kilonewtons times the load factor would give us a magnitude of the factored load of 24 kilonewtons. And then the area required is calculated by dividing the factored force to the yield stress of the material, 280 megapascals. And we require an angle having a cross-sectional area of at least 85.7 millimeters square. We go now to the table, and we will select the angle, the next angle that has the area just higher than what is required. That would be an angle 25 by 25 by 4, which has an area of 184 millimeters squared, which is of course larger than what we require, which was 85.7 millimeters square. So we should be okay from a design perspective, but again, remember, the angle that you select must have an area just higher than what is required, not by much. Again, in this question, the first part was an analysis problem in which we just calculated the stress and the elongation based on the specified forces, no load factor included. The second part was a design question where we had to calculate the factor forces using the load factor. So thank you very much for watching these examples, and of course I will see you again at the next lecture.